right, hopefully you've given this problem a try. I'm going to walk through the solution now. Um, so here is a phase diagram for methane. And the first part is just, let's label this thing. Let's label it with solid, liquid, and gas. So our solid is going to be here. This next region is going to be our liquid phase. And this bottom region is our gas phase. We could also label the triple point and the critical point. So right here is our triple point. And right here is our critical point. All right. So B is asking us, what temperature and pressure do all three phases exist at the same time? Well, when we have a solid, a liquid, and a gas at the same exact time, you're really going through a phase transition between all three. And so that's at our triple point. So if this is at our triple point, we can use our diagram to see that that's at a temperature of 90.6 Kelvin and a pressure of 0.092 atmospheres. Above what temperature can methane not exist as a liquid? All right. So it will not be a liquid at high. So if you look at how high our temperatures are, right, it's going to be above, right? So it can't exist below 90.6. We will only have solids and gases. We won't have a liquid. But that's not really like that doesn't that's not what we're talking about because that's below. So it's really referring to the critical point right here. So above that critical point temperature or pressure up in this region right here, we have supercritical fluid. So that means that we won't be able to have a liquid above that critical point. Instead, we'll have that supercritical fluid. So this will be at the critical point, which is occurring at this 190.7 Kelvin for our temperature. All right, so what temperature change estimated would be necessary to condense methane gas that's initially at 150 Kelvin and 1 atmosphere? So let's go find our 1 atmosphere right here. So we've got a nice line for it. Our 150 Kelvin is going to exist somewhere above in the gas phase over here, somewhere in between these 2 points. So let's call it about right here. So what change do we need to make? And we're going to be looking at temperature change, right? So just in the temperature scale. So we're going to be going along the x-axis. So to go from 150 to this point right here where we'll go through that phase change. And so that phase change is going to occur at 109.1. So we know that we need to get past 109.1. We're starting at 150. Right. So the difference between these two is going to give me that temperature change that I need. And so that's going to be about 40.9 Kelvin. And so we'll need to have a change in temperature a little bit greater than if everything's going to go to the gas phase, or sorry, the liquid phase. We need to be a little bit above 40.9 Kelvin for a temperature change, and it'll be a decrease in temperature. All right, let's move on to E. So what pressure change would be necessary to evaporate methane liquid that's originally at 90.7 Kelvin and 0.5 atmospheres? So looking at our graph, here's this 90.7 right here. So it's going to probably put us somewhere in this region right here. Let's call this 0.5 atmospheres and 90.7 Kelvin. So for a pressure change to evaporate this liquid, we really need to look at what is the change that's going to go from here all the way down to this liquid gas phase change right here. So it looks like that actually occurs pretty close to this 0.092. So we're going to estimate it's around there. Again, we're just estimating. And so for this one, then we're really going to be estimating our 0.5 atmospheres minus 0.092 atmospheres. So it's going to give me something like 0.408 atmospheres change. And so really what I'm going to want to do is to answer this question is I'm going to want to decrease by a little bit more than 0.408 atmospheres, roughly if we're going to estimate.